For RT, vector RT, vector function. Oh, this one they give. This one I'm going to give you in the IJ format. Yeah. They'll switch it up in the problems. This one's just a two-dimensional vector here. I've got some of those. And so, number one on this, let's sketch the curve with this vector function. And so the curve there we're talking about would be x equals what? X equals t squared, just the I component, and then the y would equal t cubed. And so it's just a parametric equation that we're going to sketch here. Goes to the origin, okay. T equals 0, y equal x and y would be 0. At 1, t equals 1, we'd have 1, 1. X and y would both be 1. T equals 2, be 4 in the x, 8 in the y. So 4, 8. Let's see, 1. If we go backwards, negative 1 would be 1 and negative 1, wouldn't we? So I think we'd be something like this. Oops. Kind of a mirror here a little bit of this. So that would go like that, and then that would go kind of out like that, but progression-wise, I think they do some arrows on that. All right. Okay. What would part 2 here? Let's find r prime of t. So the direction, the derivative function, vector function for vector function r would be what? Well, if we keep it in the IJ format, just the derivative, 2ti, 3t squared j. Really pretty simple. All right, then the third one, kind of tie the two together, number 1 and 2 together. So let's sketch the derivative at 2, derivative vector 2, and the tangent vector. Oh, sorry. I want you to sketch two things. Sketch the vector function, position function, they call it. Position vector. Get it down here yet. Sketch the position vector R2, and then the tangent vector R prime 2. Yeah, so this is just the curve associated with the vector function. What's the actual position vector? R2. be 4, 8, right? 4i plus 8j, which we've already got the terminal point denoted there. So that right there would be R2. So the actual vector associated there is that vector with the terminal point for 8. And then R prime at 2. Well, you plug in 2 there, you got 4i plus 12j. And so we could put it here, we could put it here, either one. Probably makes more sense here. So we've got 4 in the I, so that would be this way. And then 12 in the J, so 1, 2, 3, 4, 5, 6. So that would be something like that, right? One way we could designate it. And we see there we got a tangent, looking pretty well tangent there at our terminal point. Okay? Any questions on that? So far, so good? All right. So let's do another one here. They word them all sort of differently. We could do the same on this one, but let's try another one here. Okay, so let's find parametric equations for the tangent line for the curve with following parametric curves. Parametric equations. And we want to do the tangent line at 3, 2, 1. So we got x equals 3t squared, y equals 2t, z equals t cubed. That's our curve. So we want to actually find the tangent line for this curve at 3, 2, 1. All right. Well, so yeah, that means our RT is just 3t squared, 2t, t cubed. And so the derivative would be 6t, 2, 3t squared. All right. And so that gives us, the derivative gives us the tangent vectors at these values. Okay. So this is the tangent vector for each individual t-value. Aha. So, but we want the tangent line, and so for a tangent line you need two things, right? We need point, which we got it, and we also need a vector. The direction vector. And so how do we get that? Yeah, and so the direction vector, of course, has got to be tied into the tangent vector. We just need to know where we want it. And like you said, how do we get to evaluate find the value of the vector? We need to know the t-value, which it's not provided. However, since x equals 3, y equals 2, z equals 1, we know those come from this equation. And so how can we, what t-value would give us that? Well, there would be a couple that would give us 3 on, for x to be 3. We could either do 1 or -1. But these two kind of tell the tale, don't they? For y to be 2 and y equals 2t, yeah, t has to be 1. It couldn't be -1. So since y is 2t and it equals 1, the t-value therefore must be value 1 to go along with the other. And so that makes our direction vector here, we need it at 1, which that means we want the tangent vector at 1. So it'll be 6, 2, and 3. So what's our tangent line? Well, that's where we use our formulas there, if you will, parametric formulas, how to get the tangent line out of the point and then the vector. Well, that's just x0 plus at, or ta. Y is y0 plus bt, and z, z0 plus ct. Because we had the point and the vector, and so a line then you get with those two things. So it'd be 3 plus 6t. Y0 would be 2 plus 2t. And z would be 1 plus 3t. Tangent line they want there. Okay? All right. Now we start doing things with vectors, add, subtract vectors. What about the derivatives? What about the rules there for derivatives? So let's talk about differentiation rules for vectors. Vector value functions, I guess. Don't know that we'll use all these right now, but just in case, come across them. All right. So what about the derivative with respect to t of vector value function u plus vector function v. Yeah, as we know, adding, no real complications there, is it? Just do u prime plus v prime, which also would include our minus. And then if we have a constant times our vector, well, you can do it different ways, I guess, but yeah, you can just take the constant times the derivative. No big surprises there. What about a dot product? Or wait, not a dot product. First of all, they mention, what if I just have a function of t times the vector valued function u? What do you think about that? Well, it's not a constant, right? Because it's varying, and so you have to. It's a function itself. It's just not a vector valued function, but it's product rule. Yeah, it's product rule. Yeah, yeah. When you got a product like this, it's not a constant. You got to use your product rule first times the derivative of the second. That'd just be the derivative of the vector valued function. And then the reverse that. Yeah, product rule.
That's not a dot.
That would not be a dot product.
Oh, that's.
Yeah, that's what I was thinking the next one was a dot product, but yeah, this is not a vector times a vector, so it's not a dot product officially. It's just a function times a vector. That's our next one. All right, d dt of the dot product of u dotted with v. And yeah, the dot product in this sense does kind of behave like times. Same deal, yeah. So take the first dotted with the derivative of the second plus reverse that. The derivative of the first dotted with the second. Yeah. So, same with the dot product. Yeah, now I think you need to do. Whoops, forgot my derivative there. Yeah, because it's a little different than doing that. And then,
What's going on with price? Now you have, and that's the product for your dot product. You have the derivative. Yeah, multiply these.
all right. They don't mention it here, not the quotient. Got the cross product. That's number 5. Our cross product of also, I guess, kind of why they use the X and the dot. It also looks a lot like the product rule. Take now, as you know, the order of a cross product does matter, and so you have to be careful on that. but it's very much like I've been writing them. That's why I've been writing them like this. Because then the second cross product, the order is the derivative of the u crossed with v. Maybe run out of room there. Yeah. No, it doesn't. But I wrote those like that because specifically for the cross product here. I think I went off the screen on. It's very analogous to the others. Okay. All right. So then the last one of these they mention, which they go through some of the proofs of these, which didn't take a lot of time to do that, but they're so much the same. I think we kind of get the idea here. All right, this one is a composite, yeah. Kind of a vector composed with just a regular function. Yeah, it's chain rule. It's chain rule. This is probably the f of t. That is kind of thinking now. That is kind of, this is different from the f of t in the actual function here. I mean the vector function. But anyway, yeah, you got a vector function, then inside of it another function. But yeah, it's a chain rule. The derivative of the vector of f of t times that with the derivative of f of t. Exactly. Chain rule. It is the chain rule. No. F of t is not a vector, it's just a function. And they don't get into the vector composed of another vector. Not here anyway. So, but like I said, we're not going to use all those right now, but it's a good point since we're talking differentiation to get those. Yeah, talk about it if we need to. All right.